I think now that you have the exams in hand, it may make a difference how you might have filled out that post-exam self-reflection study. So I think I'm going to post a new survey version of that. I'd like you to go through your exams and then readdress that. Is there anything else directly?
As far as your...
Yeah, as far as what you thought you did or didn't, how well you thought you did and how well you actually did, and what might be, in fact, things to work on.
Is that going to be included in the...
It won't be included in the district-wide survey. It's more just for you guys. And the reason it won't be is that I don't know how other instructors are opening that post-exam survey up. So I wouldn't want to double count. I think in future to use it, I won't post it till after exams are back.
Okay.
Because my theory is always, and this was just always me, I knew what I did right and what I did wrong. Even if I faked an answer, I still knew if I didn't understand it. And so for me, I can fill out a post-exam and say, I did like crap. Even if I ended up getting a good grade, I know what I didn't understand. Right. Which is why I just sent it out as a post. Right. Just because you get a grade doesn't mean you did as well as you should have done. Unless, of course, your standard's low. Right? Bottom line is, you know, you filling out answers, that doesn't mean you understand anything. And that was basically how I approached it. But, that being said, with the Gauss's law problem, and yes, there was a Gauss's law problem, though it wasn't always obvious it was a Gauss's law problem, the concentric sphere problem. You know, that might have been one where you thought you understood it, and then you realize, oh, okay, I didn't. I totally approached it differently. So certainly those might have been points that you would have assumed you did better than you did. So I think I want to do that because the main thing is, and the whole point of this was less what the data means to us and more just, you know, what can you look at constructively and move on from it. Because ultimately it's one exam. In the worst case, the average score being 15 out of 20 means, or 14 out of 20 means basically anybody that was in the average or above, and the average means pretty close to mean, has still a chance of getting an A in the class. Right? It means you've lost on average 6 of your total points. So it's not the end of the world, it's one exam, but we have to learn from it. Right? And that's always the point. That's why there are 3 exams, and that's why the project becomes so pivotal. So, to that end, as we talk about the project, I want to point something out here, and it better be obvious. If it wasn't obvious, then you're going to have to readdress what is considered obvious. Some of the papers were heavier than others, both mathematically and purely in terms of size. Understand that the thinner the paper, the more assumption of background, context, understanding, and theory. Right? It's not just, oh, well, they just did this, they knew all this stuff from the chemistry book, and now this is how they made the nuclear reactor, right? I mean, there's more impetus. In the end, it's quality of work and content of work, and you are both rated by your peers, in part, and also by me in terms of how everybody does. So skating on a project that looks easier, and I'm not saying anybody's skating on a project, but given that of the 5 groups, 4 of them immediately went to one of the nuclear reactor papers, that tells me, oh, that's probably the thinnest paper. That's a good one to start from. And I'm not saying that that's the case, but I'm saying to the extent that that is, you're setting yourself up with that perspective to absolutely flame out. Okay? So I'm just pointing that out. The papers that are more fundamental, you've actually got more meat to work with. And it takes less emphasis on having to go back through and understand what Fermi was doing prior to establishing his nuclear reactor. Okay? And I'm saying that to warn you, not so that you don't get screwed come final day when you've got your project is 5 slides and somebody else is going through all this entropic analysis of black body radiation to determine photon energies. Okay? I mean, it will ultimately affect quality of work and in the end, outcome. So the Fermi papers are in there. I almost thought of piecing them together as a single paper to minimize the potential misunderstanding with a thin paper. But as it is, just understand that there's going to be a different type and level of scrutiny on that type of paper compared to Einstein's relativity paper. Right? Any experimental paper has that basic pitfall, if you will. Okay? So, all good with the papers. I need to get your guys, I can't remember the paper I give you. I know what it was at the time, but I just needed input for you. And I think I sent the email to Adrina, but she never filled it out yet. So just so you know, I want to get that. So you're welcome to keep the papers, and it's all good, but just be aware that, right, what is it, 15% total grade? That's 20%. You can kind of see what's going to be expected in terms of the emphasis for the quarter. So, I'm always practical. There's no shortcut slash loophole in the process. Okay, so just want to make sure that we're straight on that. Okay, and to that end, talk to me about things that you might be questions or comments about it. So don't put yourself in a black box. I'll be as much of a resource as I can, at least to try to point you in the right direction in context. Otherwise, Wikipedia has so much information, but understand you're going to be responsible for as primary understanding as possible. Anything you read online is us looking back, not the context looking forward. And there's a huge, huge difference. What we think we understand now is not what we thought we understood in 1920. And that's part of the exercise. Otherwise, it's a book report. Yeah. Okay, so make sure that I graded everything correctly. I really recommend going through these problems for yourself, okay? Because so much of everything is just sort of premised on this first idea. Gauss's law, calculation of electric field, and even the analysis of data. So, okay. We need to talk about electric potential today. And the two perspectives or ideas associated with this whole electric potential business is, to begin with, context, right? So much of what we're doing is about context. First of all, the term electric potential, now we'll use it in a context that doesn't imply that we need to worry about this at some point in the future when we get to electric circuits. But fundamentally, the idea of electric potential is potential energy per unit charge. Okay, it's normalized electric potential energy, but it's normalized to unit charge. So it is, typically I would use the letter UE. And as engineers, so much of what you end up using in a practical sense, whether it's in structures or strengths of materials or otherwise, tends to be just normalizing relationships, so you don't have to have specific data, yet you can still analyze a particular mechanical system. So this is ultimately nothing particularly new in that sense. So if you're at some point in space, then point out here, point P, and you've got some charge out here, then that charge would have a corresponding electrical potential energy based on the other charges around it and the electric field that it ultimately resides. But if you divide through by the charge, then that electric potential quantity is a constant regardless of the charge that you put there. This is the external, this is the placement of something into an environment. This is the environment itself. The second thing to say about electric potential, and this is helpful, is that it's a scalar electric quantity. That's huge, because we don't have to directly deal with vectors until creating an electric field equation or relationship out of it. So anytime, as a general rule, you can deal with scalar quantities, it's usually easier to handle than vector quantity. Which is why physicists are so compelled to use the energy interpretation of nature. Now, in terms of the interpretation, we've got two possibilities as far as how we approach the electric potential. First of all, what we say is that the electric potential difference between 2 points in space if we've got P over here, and if we've got some other point, Q over here. Potential difference in space, or between two locations, if you will, is related to evaluation of path interval, if you will, following the electric field as it relates to movement. As you step from where you start to where you end up. So I will point out that this is really whatever the final potential is minus whatever the initial potential is. Right? That's always changing in V. Ultimately, this quantity then is related to where you start and where you end up when you evaluate this E dr integral. Now understand, this is the equivalent of evaluating force over path to calculate work. So the analogy between potential energy and potential as a construct is the same analogy when you calculate potential difference and relate to the work associated with moving something from some place to some other place. You're just dividing out the charge. Again, that way you can get everything about how the space interacts in a general sense with any particular charge without having to know what particular charge you're putting somewhere. So the path might be something like this. But ultimately, at any given point, we could say, look, there's a dr as we're moving along, and there's a certain electric field at this point, such that we can take the scalar product between this vector and the electric field, and add every possibility up along the way as we go from one end to the other. Okay? So, to this end, I'm just going to assume that there's some electric field out here. And it's the relationship between a step of movement within that electric field and this location, which is different necessarily, potentially, pardon the pun, than any other location. That's why you have to evaluate over the whole path, and E is typically an equation in terms of position. So an example of this might be moving somewhere around or near is probably a better word, a point charge. So we got a point charge. And that point charge is, let's call it Q. Not Q naught, but Q, just some point charge. And the electric field associated with this point charge would be positive. Would have some basic radial electric field. And we would say, no matter where we are, that the electric field at any particular point, say R, would be related to the charge in question divided by 4 pi epsilon naught times R squared, how far away you are at that particular point, pointing in the direction of R. So in other words, if I'm up here at some point, then my R vector would be pointing this way. So my electric field out there would be radially outward with a magnitude of Q over 4 pi epsilon naught R squared. Now, here's the thing. If I start here and then move somewhere else, and just to keep it simple, let's move in a straight line. If this is position 1 and this is position 2, I start there and I end up over there. So then the question becomes, at least to approach it this way, what is the potential at position 2 minus the potential at position 1? Again, the way we would calculate is final minus initial. So we would say V2 minus V1, there's your delta V. Should be equal to minus Q over 4 pi epsilon naught R squared. As long as I stay along the same line, from point 1 to point 2, I won't have to deal with cosines and sine relationships. I can just write it this way without having to deal with any vectors and evaluating this thing. In this case, I'm left with wherever I was there and whatever it is somewhere out further away. This is what I mean by E is ultimately related to, or a function related to R. Because typically we calculate the electric field at a particular position, so relative to how far away we are. So just sort of continuing along, we can bring out constants, and we're just left with evaluating the integral of dr over r squared as we go from 1 to 2. Because it's an r to the negative 2 power, you end up getting minus 1 over r as your general solution. Oh, So in which case, these go away, and we're left with Q over 4 pi epsilon naught R2 minus Q over 4 pi epsilon naught R1. We had numbers. That would be the direct solution, or the equation to solve the problem. Now, to this end, though, with point charges only, if you recall, we can calculate, or we can assign the absolute electric potential by comparing the potential somewhere to its potential at infinity, which is a strange, again, it's one of those strange abstract notions, far, far away, if you will. But the implication here, so V1 and V2, we've already, have we looked at it? I think we did, didn't we? We talked about a point charge. This would correspond to the assumption that V2 is in fact equal to Q over 4 pi epsilon naught divided by R when you're looking at the potential due to a point charge. And the absolute value of the potential at the original location is Q over 4 pi epsilon naught R1. And the assumption is, when you treat it this way, the assumption is that with reference to a far, far away from that charge, the electric potential is 0. So, in a sense, by calculating a potential as a particular value at some point in space and comparing it to, by comparing it to 0 far, far away, it's kind of the equivalent of saying that when you're in an electrical circuit, your voltage is 5 volts at somewhere relative to ground, relative to some arbitrary, what we're calling 0. So this is like grounding a circuit. Now again, it's abstract when it's not charge moving in a wire and you're thinking out in space, but it's the equivalent thought analogy. And that's the key, is that we're not treating anything different, but by approaching charges before going to current and electricity, it seems different than it is, but it's not. You can sort of follow the context and the methodology carefully. So that's the secondary idea. In other words, or the tertiary idea, I guess, if you know an electric field and you're looking along a certain path, the potential difference is essentially the evaluation of the work to go from one point to another along a particular path, divided by charge, per unit charge, if you will. Again, work per unit charge, energy per unit charge. Okay? And the textbook seems to focus on that one in particular. So, if you know the electric field, you calculate the potential difference. I should clarify, the units of this thing are intrinsically or implicitly joules per coulomb. Okay? So we start slopping around with new letters and new units, but understand that the implicit understanding of potential difference or potential as an absolute at some point in space is in fact energy per unit charge. And when you start combining things like electrical current, resistance, and all these other things, you start seeing these implicit capacitance, right? Coulombs per volt, coulombs squared per joule. You start seeing that there's all of these little implicit relationships which tell you something physical that aren't very obvious when you look at point charges in space, and that always ends up being the problem. This is a very abstract concept that we approach it when we end up approaching. So I'm just going to make a note here that if I there's your R. I'm not changing anything. Everything I said is going to play out that Now, the third idea to this, fourth idea, fifth, sixth, whatever. Right? It's an infinite series, right? Selectively keep it a bit. Is it referring back to this point here and reversing the interpretation of this? What we're left with is that you can calculate an electric field in terms of this much simpler electric potential, if you can determine what that is, or if you know something about it. By looking at how the electric potential changes in space. In vector calculus, we would say the gradient of the electric potential in space. How is it changing? And the direction of this would be pointing in the direction of R as you're looking at how the change is changing in some particular space. So, the gradient. Yeah. And remember, R is X, Y, and Z, if you will. Another way of saying this is basically that E is, in gradient terms, this. Have you seen the gradient or the del operator? Have any of you seen it? It's a shorthand notation, so you start throwing more notation because it simplifies and makes problems shorter to write. But really what it means is that this, what we call the del operator, is a way of saying that if you take the derivative, and it's a partial derivative, I'm going to write it as a whole derivative because for anybody that is not comfortable with saying a partial derivative, it's taking the derivative of a vector or of a function with respect to x, and that's its function and that's its value along the x direction, plus the derivative with respect to y, plus the derivative with respect to j, or k, z, k, whatever. It's an operator that looks like this. In other words, it's just implying that you look in 3 dimensions instead of, it's not necessarily always along one line. When you have 3 dimensions, then you just take the derivative with respect to x, y, and z, assuming that this is specified in x, y, and z, for instance. So then, if you know a potential in this form, then taking the gradient of this potential is just another way of saying dv dx, the I direction, plus dv dy, j direction, plus, if it's specified, so we're not going to worry about that, and that's not what I'm going to throw in an exam for the 5 people that are in class today. But what's important is that's how you'll see it. And it's a vector operator. Instead of a vector as having a specific value, it's now an operator, kind of like a derivative or a square root function. It's just a vector function that you apply to some other quantity. So anyway, this is what it is. So you'll see it as some place of shorthand notation, but it just means how is the electric field out here somewhere? How does it vary in space? If the voltage is here somewhere, and it's here somewhere, how is it varying as you step from some point to some other point? And you look at the derivative of that function. Nonetheless, that's what it is. And so sometimes, if you have a specified or an easily calculated electric potential, which is usually the case with point charges, then taking the derivative in space, x, y, or z, will allow you to obtain the electric field directly, rather than sometimes having to take the long form to get it. So these are the key ideas behind this electric potential. So we've looked at this example. How are we doing for time? Let's look at an example that might strike close to home. What's the electric field due to a combination of, or a pair of two point charges separated by a certain distance? And we'll use the electric potential to maybe figure out what the electric field is. Or electric field. By the way, did we look at an atom and a voltage, electric potential for an atom?
I don't think so.
Okay, so we'll come back to that one after break.
We looked at electric force on that.
Okay, yeah, well, I know we did that before.